So last time we were talking about transfer functions, and we drew. So first we talked about transfer functions, and we sort of drew some random transfer functions for random functions, and then we sort of said, okay, let's draw some useful transfer functions. So we drew the transfer function magnitude and angles for the low pass filter and the high pass filter, and we drew them on a linear scale. Just we drew these, for example, this was a transfer function for the high pass filter, and we just substituted various numbers for f, for frequency, and we plotted the corresponding magnitude. So we just substituted various values for f, and we plotted the corresponding magnitude, and then we did the same thing here, substituted values for f, and plotted the corresponding angle. So that's what we did last time for the low pass filter and high pass filter. Sometimes we would like to design, for example, a filter that cuts. For example, that is a high pass filter between 0 and 4 FB, for example, and then after that it's acts as a low pass filter for frequencies beyond that. So something like a band pass filter from 0 to 10 FB, for example, right? So the scale for on the frequency, the x-axis is going to be too large to draw in a single plot, for example, and sometimes it's nice to be able to represent something like that using a log scale, because what the log scale does is shrink the the corresponding axis. So if you draw these frequencies on a log scale, instead of having in the same sort of area, you will be able to fit nicely something along the lines of 5,000 FB versus 5 FB, for example, right? So it's just a visual effect, right? So there's nothing, it doesn't really add much difference besides the visual effect, and the visual effect becomes very pronounced when you're designing filters at frequencies that are close to each other. So we just want to be able to draw these magnitude and phase plots on a logarithmic scale. That's basically what we're going to do next, and it will just add some value. And what we saw last time was I talked about moving, for example, the way we will move these magnitude and phase plots to log plots is we will take the magnitude of the transfer function h of f, and we multiply it by, and take the 10 base log of that and multiply the magnitude and that by 20. This results in a unit called decibels. And I sort of talked to you about decibels in terms of noise, for example. And we said, I told you that something like what you're hearing from this thing here, I think the fan that's inside this cabinet, would be about maybe 60 dB, 50 dB, something that you can hear. It's not annoying, but you can still hear it. Similar to, and I showed you the example of a transformer. These transformers that you have in these distribution substations or small buildings outside your compound, a couple of compounds that are used to transmit, take power at higher voltage, step them down, and transmit power to your homes. You pass by that, you will be able to hear it. It's not annoying, but you'll be able to hear it. Yeah, I showed you some specs for the noise from a transformer, and we saw that 50, 60 dB is something you can still hear, but not annoying, right? So something similar to this. Yeah. So that's just to give an idea of this, the dB sort of measure or scale. Yeah. So we would take the magnitude plot, magnitude, and do this to it. If I want to turn this off and not have it come back, quit this thing, okay? On the frequency scale, what we would do is just take the log of the frequency and write and we typically have units either in 10 or 20, 10 or 2s, like so, either between each axis or between each grid point, you would typically have a difference of either multiplication by 10, like between 10 and 100, or 2, which like 500 and 1,000. So, and we gave those sort of special names as a between for multiplying by 10, if there's a 10-step change between 10 hertz and 100 hertz, we will call that a decade. And if it's a 2-step change or a double, twice the amount, 500 and 1,000, we will call that an octave. And why we need that? It's because sometimes the magnitude, so we're drawing the magnitude against the frequency, and they are both going to be in log scale, right? And sometimes the magnitude will change by a certain amount in an octave, or the magnitude will change by a certain amount in a decade. So this slope, the slope that we will give is going to be magnitude versus frequency, right? So that's why we will sort of typically give the magnitude versus frequency as, for example, the magnitude will change in 20 dB per decade, or 20 dB per octave, or 40 dB per octave, or 40 dB per decade. That's the reason why we sort of use the terms octave and decade here. So this is how you do change the magnitude plot to the dB, and this is how you change the, so you take the log base 10 of the frequency. So you take the log base 10 of the frequency, so this is the number of decades. So this axis is basically the log base 10 of the frequency. And this is the 20 times log base 10 of the magnitude. So let's see how we use this for the low pass and high pass filters. So we talked about the transfer function for the high pass filter before. So this is the low pass filter. So we derived this before, right? And this FB was 1 over pi RC, 1 over 2 pi RC, right? So this is something known. This is depending on the circuit that you have in the system, and the only variable that we have here is F. So, and we came up with the magnitude, we drew the magnitude and phase angle of that before. What we're going to do now is take the magnitude and phase that we came up with before, and basically just apply this equation to it. So take the log base 10 of the magnitude and multiply by 20. And so if you do this, these are two numbers on top of each other, so I can take the log of the top one minus the log of the bottom one. So 20 times log 1 minus 20 times log of the denominator. And log 1 is 0, so you end up with a negative number. Remember when I was plotting, and one student, I believe, you were mentioning you were plotting it in positive, why is it negative? So there's actually a way, so you actually draw everything in negative. So there's a way, a standard way to actually do it. So, and it comes from the math that we have here, right? So the negative comes from the fact that in the numerator we have 1 for the low pass filter here, and you end up with minus 20 times log of whatever was in the denominator. This square root you can bring outside, and you can bring down here from your logarithmic identities, and you can rewrite this as the magnitude in dB will be equal minus 10 times log of this function, right? And now all I need to do is substitute with numbers, right? So for very low frequencies, f is 0, for example. If f is 0, then it's minus 10 log base 10 of 1. So the magnitude in dB will be 0, right? So I know at low frequencies, I start at 0. And I know my low frequencies, I start at 0, right? And then how about at f much larger than fb? Log base 10 of a large number. Log base 10 of a large, just put some large number in a calculator, take the log of it and see. Should be what? It should be, I mean, it will be a minus 10 base 10 log 10 of a large number is a large number, right? But because we have a minus sign, then it's going to be going negative, right? And if you keep adding numbers linearly, you will see that keep adding numbers linearly, but then you sort of put them on a scale, a logarithmic scale, you will see that they will just maintain a certain slope. It will be a linear change in magnitude with frequency when you draw the magnitude on a log scale, right? So what we end up with is is something that is zero at low frequency and has a certain slope at high frequencies. So, and these two lines meet at a certain point, and it just happens to be FB. That's why FB is a very important, is how you design your circuit, right? We saw that FB is equal to, what, 1 over 2 pi RC or something? Yeah, 1 over 2 pi RC, right? So FB is how you design your circuit, because FB is the this break point where this filter now starts to attenuate the signal if it's a low pass filter. And it will be the same point where the filter will start allowing the signal to go through with a high pass filter. So this point here, FB, is how you design your circuit, right? At the low, this will let everything below FB pass through with a decent magnitude, right? With a decent magnitude. So the magnitude B will be close to 1. Remember, it's 10 log 1 is 0. So this will pass through with a magnitude or gain of basically 1. We'll go through this, come out the same, right? Because in dB it's 0, on a linear scale it's 1, right? So it will go through, and then here it's attenuated. So that's why FB is an important consideration. And we know that at FB, if we do a number, point by point, we will see that, of course, at FB there's the magnitude is a little less than 1. How much less we can, if you substitute in, you will see that at F equals FB, then this is 1 squared, so 1%, so 2, so log of 2 is what? Log 2 is what? Log base 10 of 2. Nobody has a calculator? Huh? 0.3? Yeah, so log base 10 of 2 is 0.3. 0.3 multiplied by 10 is 3, minus 3, right? So you see here that the magnitude will be about minus 3 at FB, right? So we just substituted the numbers. So everybody's okay with this? And that's what this means here. The actual plot is an error of 3 dB at the corner or half frequency FB. It's not an error. This is the actual value. But because the next thing we will do is when we design these filters, we don't want to go and draw actual values and calculate actual values all the time, right? We would like to draw asymptotes to the filter. So I know that I need, for example, I have an electrical signal or some signal that I want to filter out high frequency content from, and I know that what I would like to see is up to 50 Hertz. So what would you do in that case? And you know that the signal has some 50 Hertz component and maybe some ripple here, some ripple here, some ripple here, some ripple here. This ripple is at higher frequency, maybe at 300, for example. So what would you do? How would you go about this? I would choose FB. I want to let through everything until 50 Hertz, right? So I would choose FB to be something fine, a little greater than 50 Hertz, maybe, I don't know, 75, for example, right? Because I know this ripple, for example, is at 200, for example, right? So I know this ripple is at 200. I know my signal is at 50, and I want it to pass through with full gain, at gain is equal to 1 at 50 Hertz. So I would probably select FB to be 75 in that case. And FB is equal to 1 over 2 pi RC. So you select your R and C correspondingly. So once you select your R and C, from your knowledge of FB, then you can draw these asymptotes. I know that until FB, the low-pass filter will sort of allow the signal to pass through. Beyond FB, it will attenuate. The attenuation for a low-pass filter will be between this point and this point. I have what? Multiplication of 10. What did we call this? When the frequency is multiplied by 10? A decade, right? So, and if you substitute with f equals 10 FB, and then substitute with f equals 100 FB, and do the calculations for magnitude, you will see that the magnitude changed by 20 dB, right? It changed from minus 20 to minus 40. So it changed by 20 dB per decade. Okay? And this is characteristic of first order filters. So any first order filter, you cannot design better than that. Right? If I have a signal that's at 50 hertz and noise that I want to attenuate at 55 hertz, right? This type of filter will not be good enough because at 50 hertz I'm here for, let's say I design FB to be 50. 50 I'm here. How about 55? Where am I? Not that this is FB, this is 10 FB. So this 1 FB is here, 2 FB is here. I'm actually at less than that, right? So I'm actually letting all the noise go through, right? So I cannot really use a filter like this if I have my component at 50 and the component that I would like to filter out or attenuate at 55 or 60. It will be useless, something like that. But how about if I'm able to do this? I'm able to make this change from 20 dB per decade to, in this case it will be 20 dB per maybe octave, right? Then this filter can attenuate signals much more sharply than a filter like this, right? But these will not be first order filters. They will not be a single R and a C. They will probably be combination, maybe R, C type of second order filter. We will not study second order filter, but the idea is I want to, you need to be introduced to the fact that the order of the filter is what is doing this. Right? So typically, whenever you see one reactive element, first order, two reactive elements, second order, three reactive elements, third order. So the more reactive elements, the better control over the slope that you have. Okay. So any questions about this? Basically, I took our magnitude, our transfer function, and then took the magnitude of the transfer function, multiplied by 20, and took its log, and plotted. There's real values, and then there's asymptotes. Typically, an engineer would use asymptotes, right? I would just use my asymptotes and design my circuit, and then I will do the experiments and go and fine-tune, etc. Why? It's because RCs are parameters that actually don't have, when you buy a capacitor, for example, I think I put the capacitor datasheet on the website. Open up the capacitor datasheet and it will tell you that the capacitance is so-and-so microfarad plus minus 20%. Right? So all of these capacitors and resistors have tolerances. Right? So if you want to buy capacitors and resistors with very tight tolerances, so you can buy resistors and capacitors with tight tolerances. So I can buy a resistor that I know is going to be within the number that I want, within plus minus 1% or 5% versus 20. But I will have to pay much more for that, because what they actually do is they don't actually manufacture a different resistor or a capacitor. They actually manufacture everything and then they screen them. So if you want a specific resistance within a specific tolerance, they will actually screen these capacitors and resistors, and you have to pay much more for the screening, for the screened version, because you want these screened capacitors and resistors that have very tight tolerance, because you designed your circuit to depend on such a tight tolerance. Otherwise, what does that mean? If the tolerance is not very tight, it means this FB is moving between here and here, for example. Right? That's what it means for the filter, which means the signal that you can pass through and attenuate is not very well defined, right? Which is okay if, for example, my signal is here. I don't care if FB bounces between these 2 points. If my signal that I want to pass through is around FB over 9, for example, and the noise content there is about 50 FB. Do I care in that case to buy a high tolerance capacitor and resistor? No, I don't. Right? So there's cases where you need to buy the high tolerance, and cases where you don't need to buy. Any questions on this? We will do the same for magnitude. I mean phase of a high pass filter. And then we will do the same for, so this is the low pass filter. Then we will do the same for the high pass filter. Draw the phase and the angle plots on in dB. It's basically what we're doing today. So for the angle plot, we start from the same point. We have our transfer function. We divide it up into real and imaginary like we did before. We took the imaginary component and we took our real and imaginary components and calculated the angle. The angle of the transfer function is inverse tan f over fb, right? So this was our angle theta that we are going to plot, and again it's negative, so it's inverse minus inverse tan because this is in the denominator, right? So it's negative inverse tan f over fb, and so we plot angle here. And of course, this is a linear scale, and then this is a log scale. So this is a log scale for frequency. This is a linear scale for angle. We're only drawing the log scale for magnitude, right? For angle, it's linear scale, and frequency is always log scale. So again, same thing. We will have an asymptote. So if you look at this, punch some numbers at low frequency. See what the angle is. You will see that the angle at low frequencies, so f, less than 10 fb, will be very close to 0. And punch some numbers at very high frequencies. You will see that numbers, for f greater than 10 fb will always be going to minus 90 degrees, right? So we know that the low frequency asymptote is here, high frequency asymptote is here, and we know that between them there's some connection. This connection between them will depend on the order of the filter, right? How steep this is between here and here, how between 0 degrees and between minus 90 degrees, how steep this connection, where exactly it happens, it will depend on the order of the filter. For a first order filter, this is sort of how it looks like. It's FB over 10, and 10 FB is sort of the asymptotes for what we for the phase angle. And this is the actual value that we have here, right? So just direct substitution, right, into this equation. And here they just discuss this idea of the asymptote. It's a horizontal line, which makes a lot of sense, right? At low, I would like to have the signal that I would like to pass through. I want it to be what? I want it to go through without change, right? The signal that goes through, I would like it to go through without change, right? And this is the same for my magnitude. At low frequency, I want the signal to go through with the same magnitude and the same phase. So it's the same magnitude and the same phase. Phase is not changing, it's 0. There's no phase shift between the output and the input, right? At higher frequencies, I've attenuated the signal. For me to attenuate the signal, I made the capacitor do something to it. The capacitor and resistor did something to it, right? What did they do? They brought down its magnitude and they had to phase shift it. By acting on it means, they did something to it. There's something to it, caused the phase shift to it to happen as well. Okay, so they attenuated the signal as well as caused some phase shift to it, right? But we know that capacitors, what do they do? If it's purely a capacitive circuit, that all it can do is change the phase shift by 90 degrees. Remember, the pure capacitive circuit, what was the angle between voltage and current? 90 degrees, right? Cannot be more, right? It's always fixed for a pure capacitive circuit. So the most that it can do is phase shift by 90 degrees. That's why these 90s and 180s will be important, because anytime we have two capacitors in the circuit, we will not. We will only do first order. But this is where the 90 degrees comes from. And same thing here, the slope of this line is if you go to this point here, for example, it's minus 45 at FB. And then it's at 10 FB, it's minus 90. So the slope is 45 degrees per decade. 35 degrees per 10 multiples of frequency. Right? So it's very important to know that for the magnitude slope is 20 dB per decade. Right? For every decade, this slope will change by 20. The magnitude will change by 20 dB. And for the angle, the slope is 45 degrees per decade. Right? So if you're given a signal, you're given a signal at a certain frequency you want to let through, you automatically go and draw your magnitude plot and phase plot. So you draw your magnitude plot F until FB here, and then you can draw this, and you can put, if you go to the scale, you make sure that this is what, changing at 20 dB per decade for a low pass filter. And then the corresponding angle will be this way. So this is FB over 10. So this is FB, this is FB over 10 here, FB, and this is 10 FB, right? 10 FB. So FB is somewhere here. This is causing the signal at FB to change by 45 degrees. Are you okay with that or not? Depends on what you want, right? If I only care about the magnitude, then this is okay. If I care about the magnitude and phase of the input signal, which is sometimes something you care about, right? If all your signals are going to come in and be filtered and phase shifted together, no problem, right? Because with respect to each other, nothing changes, right? But if you care, for example, in a power system, for example, we care about when something specifically happens. So when something specifically happens, that means I need to make sure that the phase angle of the signal that's coming in is not distorted at all. So I would make sure that I design a filter that has no phase shift until the signal, the frequency of interest, right? So then I would use a signal with a frequency of less than FB over 10 if I don't want any phase shift. So good practice would be, yeah, you would design a low pass filter. You would choose your cutoff frequency. This is called cutoff frequency or break FB. It's called your cutoff frequency or break frequency, right? So your cutoff frequency here, or corner frequency, or half frequency, too many names. Right? This would be 10 times greater than your signal of interest. That's a good sort of engineering choice, because then the magnitude is unity, does not change, and the phase also does not change. And here they just talk about asymptotes. So these are the magnitude and phase plot asymptotes for a low pass filter. We talked about those briefly. So any questions on asymptotes, actual, difference between asymptotes and actual values? They're just approximations. See how far, how the signal has changed. Back of the envelope type calculation. And we do the same for high pass filters. So we have the transfer function that we've derived before for the high pass filter, and we do the same. Take the log base 10 and multiply by 20. Here we have something on the numerator and the denominator, so the equation is a bit different here, right? So we can now substitute with small values. For f is 0. F is 0, what do you get? This log 0 is, so f is, yeah, log 0 is what? Log base 10, 0. F is 0. What is log 0? Calculator. Huh? Huh? Log base 0 or log base a very small, log base 10 of a small number. Small number, log base 10 of a 0.1. Of 0.1. Minus infinity of 0.1? Minus 1. So it's a negative number. So it's negative number, you multiply by 20 will still be a negative number, and then you do this. So it's we said this is small, f is small, so this, let's say this is 0, goes away. The log base 10 of 1 is 0. So we know that this is sort of going to be what's going to affect at on the low frequency end. So we know on the low frequency end we're going to be attenuated, right? It's a negative large number, right? So we know that we will be attenuating on the low frequency end. And on the high frequency end, f is much greater than fb. What will happen? Log of a large number. What's log of a large number? 10,000. Or log of 10,000 is what? Log of 1,000. what? Log of 1,000. It's 3. So, and then this as well. This is a large number as well, right? 1 is insignificant. F is much larger than FB. So this is also log of a large number. So it's, and then it's what? It's very close to 0. These are two large numbers. So you're subtracting two large numbers. So the difference is going to be very small here. So practically, basically 0 at infinite, at F is very, very large. So that's what you have as the asymptote at high frequency. You know that these are two large numbers. You're going to subtract from each other. The difference will be pretty much 0. And at low frequencies, you know that this is a large negative number, right? So of course, you have to substitute the specific values, and when you substitute the specific values, then we will be able to find the slope of this line here. The slope, again, for the first order high pass or low pass filter, we know that the slope will not be more than 20 dB per decade. Since it's first order, it's always going to be 20 dB per decade. So if you look at here, this is a decade from FB over 10 to FB. It changed from 20 dB or minus 20 dB to 0. It's always 20 dB per decade for a magnitude since I have a first order filter. Okay. Alliance for 20 dB per decade. And it still has, of course, and it will have the same actually 3 dB at F equals FB. So if you substitute with F equals FB, you will still find the log to be 0.3 multiplied by 10. There will be a 3 dB difference between the asymptote and the actual value. It's exactly the same as the low pass filter that we did before. Angle is also very similar in shape, so it's still a minus 45 degree per decade. This slope here is a minus 45 degree per decade, and it goes from 90 to 180. So there's a change of 90 degrees as well. 90 to 180. This is 90 degrees, and this is 0 degrees. This is 90 degrees. So there's a change of 90 degrees because you still have one capacitor. So capacitors, what do? Capacitors are open circuits for DC. They are short circuits for AC, right? So they are gonna act on some signals that are AC in nature, and they will not act on DC signals because they will be an open circuit in nature. When they act, and they are the dominant component in the RC circuit, they will phase shift the quantities by something close to 90. When they don't act on the signal, they will not phase shift the quantities by this 90 degrees, and the quantities will end up having a phase shift of 0 degrees because what's dominant there is the resistor, since the capacitor is an open circuit. Right? These are all RC circuits. So the capacitor will either be phase shifting or dominant and acting on the AC signals, or the resistor will be dominant and the capacitor will be an open circuit. And that's why we always see either a phase shift of, at the asymptotes, 0 or 90, for the low pass and high pass filter. For the high pass filter, it's 0 where? At high frequency. Right? Forget about all the math, right? If you want to draw the asymptotes, for the low pass filter, magnitude and phase. At low frequency, what is the low pass filter doing? The low pass filter would like to pass the low frequency signal through as it is, right? So at low frequency, I expect that the phase shift will not change because the signal wants to pass through as it is. And then at high frequency, again, it's an RC circuit. So since it's an RC circuit, I know that at some point the capacitor will be the dominant component acting on the AC signal, and it will phase shift the signal by 90 degrees. So I know that this is what's happening. Right? And I know the slope of this is going to be 45 degrees per decade. And for magnitude, it's a low pass filter, so at low frequency, it is allowing the signal to go through with 0 dB gain, meaning a magnitude of 1. 0 dB gain is a magnitude of 1, and at high frequencies it's attenuating the signal. It's a single first order filter, so the slope is 20 dB per decade. So this is 1 decade. This will change by 20 dB, minus 20 every decade. And for a high-pass filter, asymptotes are just the opposite. At low frequencies, attenuation. At high frequency, it's 0 dB. This is magnitude in dB. And angle, at high frequency, I would like the signal to pass through as it is. So I expect that I design the circuit such that my angle at high frequency is what? 0 degrees. And at low frequency, the capacitor is attenuating. There's an attenuation, right? This attenuation is due to the fact that you have a capacitor in there. It's not due to the fact that you have a resistor. Resistors don't do much, right? So they're time constant, basically. But what is doing the action of attenuation is the fact that capacitors are able to change from short circuits to open circuits. So when they see something they don't like, it's an open circuit. They see something they like, they let it through. They play with it, right? So then at low frequency, we have one capacitor, so at some point it will be able to shift maximum by 90 degrees. And then there's a connection between them that depends on the order of the circuit. And this is also at the same slope of 45 degrees per decade, and this is also at the same slope of 20 dB per decade, because we have one capacitor. Okay, so very similar, high pass, low pass filter. So any questions on this? So this is the magnitude plot of the high pass filter, and this is the phase plot of the high pass filter. And notice that it's, when you do when you calculate the angle, this ends up, being 9t minus a certain value, right? So, and hence these are positive numbers, versus in the previous one, for the low pass filter, it was negative numbers, right? The angles were negative, right? The axis was in negative degrees, and here the angle is in positive degrees. So one of the filters is actually delaying the signal, and one is actually advancing the signal versus the input. Okay, so one is causing a positive phase shift, one is causing a negative phase shift with respect to the input signal. V input versus V output. H is V input versus V output. The angle of V input versus V output here is being advanced. So V input versus V output, the angle is being advanced for V output. In the low pass filter, the angle is being delayed of the output signal versus the input signal. Now some examples I think that will help. So we have a first order filter, a first order high pass filter that has a transfer function magnitude of minus 30 dB at 60 Hz. Okay, so this is a high pass filter, so let me draw the magnitude plot. So what does the magnitude plot for the high pass filter look like? Magnitude plot. Attenuation at low frequency, right? And then at high frequency it's 0 or no attenuation, 0 dB. Right? So this is the magnitude plot of the high pass filter. They're saying that at 60 Hz this has minus 30 dB magnitude. So let's say this is 60 Hz, minus 30. This is dB. And find the break frequency for this filter. So this is minus 30 dB. What do we know about high pass filters? We know that the slope of this line is what? What's the slope of this line for any of our filters? For the low pass or high pass? 20 dB per decade. right? So this is 60 hertz at f equals fb, magnitude is 0 dB. Yeah, I don't know if that's a given or not. I'm assuming that's I assume that's a given at f equals fb. We have 0. So 0 is happening here at f equals fb for this filter. So this is f equals fb, and this is f equals 60 hertz. A straight line body magnitude has a slope of 20 dB per decade. So this is if I go fb over 10, right? If I go fb over 10, if f equals fb over 10, what do I expect to be the magnitude? If at fb I have 0, what do I expect to see at f equals fb over 10? fb over 10. So this is, it's 0 at f equals fb. fb over 10 is 1 decade less than f equals fb. Right? So 1 decade less, what do I expect the magnitude to be? Minus 20 dB. So minus 20 dB will be 1 decade later. Right? This is minus 20. This frequency will be f equals fb over 10. So this is definitely, so that my point of interest is definitely more than 1 decade later. So how about 1 decade more? It will be minus 40, right? So I've passed the point of interest, which was the minus 30 dB. Where does this minus 30 dB fall? 1.5 decades before f equals fb, right? So 30 dB per decade, 30 dB over 20 dB per decade, which is my slope, is 1.5. So 1.5 decades before f equals fb, I have my magnitude equal to 30, minus 30 dB. Right, so what are they asking for? Find the break frequency for this filter. So I know this is 1.5 decades, this is okay. And but they should have stated that, you know, at f equals fb. I mean, for me, I don't know if this is part of the problem or part of the solution, right? And for me, this is something that they should include in the question that they posed. So if they do that, then we know how to do until here, right? And then this log fb over 60 is equal to 1.5 decades. Yes, that's fine. So fb over 60 equals 10.5. So they're using this equation. Number of decades. So they're using this equation. So my number of decades was 1.5, and I have one of the frequencies, and I'm trying to find the other one. So I'm trying to find fb and given one of the frequencies, right? So if I go back to the example, I'm trying to find the break frequency of this filter, given that the frequency or the magnitude at 60 hertz is 30 dB, minus 30 dB. So I calculated the difference to be 1.5 dB per decade, 1.5 decades. I substituted in that equation, and I was able to calculate FB. And you were able to calculate FB, of course, is in hertz. So your break frequency for this filter is 1900 hertz. So starting from there, you can select the specific R and C for this specific filter. So we'll continue the rest of the examples next class. So, yeah.